Yeah, okay. So,
Just 1 minute.
oh, okay. Yeah. Mhm.
Okay, so let me open the files. Okay.
Oh, okay. Okay.
Okay, so we were here, right?
Mhm.
So what discussion we made, if you remember, can you tell me what we did? Okay, do you remember what we did in the previous class? Okay, I'm going to check it from my file. Okay. And also we can go to recordings. Okay, we are done with the meshing. Okay. So we are done with the meshing part. Okay, so meshing part is done. I was discussing that the only difference between this mesh over here and the mesh I'm showing there is, I think they're almost same. They're almost same, right? But if you take a look on this picture is slightly different. If you take a look here, the picture I've shown on the my main slide and the picture here, they are different. See that it has the like right now the in our current case the our mesh density high is in this region, but in this mesh it is like almost up to outlet. Okay, you can extend the region, no problem. Okay. Uh, like I can go back to my geometry software. Okay. And I can extend the region anytime, no problem. Okay. And making two regions will be beneficial because now we can adjust the two element sizes over there. Okay. So for that to change, we just need to go to the plane number 4, I think. Scale number 7. Make this dimension as like maybe 6,000. Make the angle maybe, okay, make it 6,500. Okay, so put a distance of this one maybe like 25,000 or 22,000. Okay, now this will be exactly same. So if you want to go with, okay, I will go with some medium value. Let's say make it like 18,000. Okay. Okay, now close the geometry and double click on the meshing. So we have to just recompute the mesh. That's the only thing we have to do. Okay. Okay, so now simply click on the mesh. Here you can click on the green tick mark and then close. Okay, so here you can click on generate. Simple. That's all. Okay.
Yeah.
Okay, then I will be updating the mesh. So it will update the mesh means that it will translate the mesh to the fluent. The last thing that it will do is it will check the mesh. It will check for any errors. The last thing it will do is like a translate mesh, is writing file in the MHS file format and then translating to the fluent. Okay. So you can close here. Okay, if you want to find out the like information about the mesh, that we can do here. So for example, the quality you can measure here. So let's measure the like orthogonal quality. So here it is showing the value of minimum is a 0.012. That's very low quality, but okay, we will go with this thing. I think the low quality will be where it is. The lowest quality elements are here. And why so? Okay, they are low quality because the length is very, very long and the angle is there. If we change the length, like maybe if we put the more cells here, we can increase the quality. But right now, this is not our target. So just leave as it is. And you can see average quality is like very high, is a 0.88. Okay. And the number of cells are 44,000. Number of cells are the 44,000. It shows that the number of cells are very, very low actually. Okay. So that thing we can see actually from here. Very obvious. Only solution is that we have to increase number of cells. Only solution is that one. Okay. So now you can close this meshing software and double click on and I would suggest that reset everything here so that we have the fresh copy of the mesh. So double click on the setup. Put number of cores to the 4. Right now I have the 4 cores only on my computer. That's why I'm putting 4. Maybe if the more, you can put the more. But I don't think that for this number of cells, we need to be putting like more than the 2 cores here. Okay. 1 is enough also. Okay, so here the data is selected based on the what condition. So I'm referring this paper. This reference is over here. You can copy this reference from here and type in the in the Google. Okay. So this is the paper I'm referring to. This one, and it was published in 2020. Citations up till now are the 5. I don't think so. This is a very good paper actually, but this is what I was referring at that time. So this is the whole paper is given here. We're not modeling the trailing edge split flaps. Okay. And if you take a look here, okay, they have the some sort of the slightly different areas for the refinement. You can see that this is like elliptical shape. We have put the circular shape here. They have put some sort of circular boundary here. Okay. This is their verification plot. This is excellent data, and then they solve the case with the K epsilon, SA, and SST. Number of cells are like a very high. In our case, it's around how much? Around 44,000 cells. And in presentation, it was around, if I remember correctly, they were around 189. Okay, it was a very fine mesh actually. So right now, I'm just making the very coarse mesh for understanding purpose. Okay. Okay, so now we have to find out the boundary conditions. The boundary conditions are given as it states that we have what we have here. The velocity at the inlet is 10 meter per second. Okay. This is given in the paper here. The wind speed is 10 meter per second. Okay. And the TSR is a 2.5. I'm solving through TSR 2.5. You can also try to TSR 3.0, but that is your exercise. So for TSR 2.5, the TSR is actually the ratio of the linear velocity, the tangential velocity to the wind speed. Okay. So this wind turbine is here. Wind turbine blades are here. And wind is coming from this direction. Okay. So the wind turbine blades are moving in the a circular path. So at every point there is a tangential velocity u, and that is equal to the omega into r. Okay. And the wind velocity is the v in or the v wind, whatever you are v air, whatever you put the name here. So the TSR is the ratio, that is the omega r divided by the wind speed. So now I'm taking TSR is equal to 2.5. So, and omega we don't know. R is equal to R the half of diameter, which is the 2.5. So half will be the 1.25, and the V in is the 10 meter per second. So omega is equal to 2.5 into 10 divided by 1.25. So I can calculate the values. And this value will be 2.5 into 10. And divided by how much? 1.25. So it's a 20 radians per second. 20 radians per second. You can directly input this value into the fluent, or you can change to the RPM. So formula, I don't remember the formula. I can drive the formula. In the one circle, we have the a 2 pi radians. Okay, and this is one revolution. So 2 pi radians is equal to one revolution. If I divide by the 1 minute, So it's a 60 seconds here actually. So I can write down the 1 RPM is equal to 2 pi by 60 radians per second. Okay, and the 1 radians per second will be 60 divided 2 pi into the RPM. Whatever RPM are there, put the value there. And so in this way, we can calculate the radians per second. And from radians per second, we can calculate RPM here. So we use this formula right now. Okay. So 20 radians per second are there. So 20 radians per second into 2 pi upon 60. So into 2 into pi and divided by 60. This is the 2.09. 2.09 radians per second. Okay, very strange. So 2.093. So sorry. RPM will be 2.093 for 20 radians per second. No, I don't think so. I don't think so. Or it should be like that. Okay, let's take the like online plotter or online converter. Okay. So just 1 minute. Radians per second to RPM. Okay, so we have the like online calculator. So 20 radians per second will be equal to how much? 190 RPM. Okay, that's why I'm saying. Okay, now let's go back. Let's go back to presentation. So I am saying that the 1 RPM is equal to this one. Okay. So what I'm trying to do is that I'm actually trying to find out the from the radians per second. So I have to multiply the radians per second with this value. So 20 into 2 pi divided 60. Okay, we have to do this thing. What do you suggest? 1 minute. 1 minute. Okay, here it is like a circle. So from this circle, we can say the one revolution is equal to 2 pi radians, right? So if I divide by the 1 minute, there will be like a 60 seconds. Okay. So dividing with the 60 second 1 minute is the same thing. It's a 1 RPM is equal to 2 pi divided by 60 radians per second. Okay. So 20 RPM will be equal to 20 into 2 pi divided by 60 radians per second. Okay, now if I want to find out the how many RPM will be there in a 1 radian per second, the formula will be that radians per second is equal to 1 into 60 divided by 2 pi RPM. So for 1 RPM, this is the value. For 20 for the 20, this is for 1 radian per second. For 20 radians per second, this will be equal to the 20 into 60 divided by 2 pi RPM. So 20 radians per second will be like this. Okay, so we were doing the formula in the reverse order. So 20 into 60 divided by 2 pi. So 3.14. This is a 191.08. 191.08. And what we were getting from the online calculator, it was 190.98. So it is like why we get the different values, because we are approximating the value of the pi, that is 3.14. But here they are, I think, using the more decimal places there. So let's keep the value as a 191. Okay, let's keep the RPM is equal to 191. So we have the like 20 radians per second. So 20 radians per second is equal to 191 RPM. This is the omega. Okay, R is equal to 1.25 meters. And also what we have, the velocity of the wind is equal to 10 meter per second. We are modeling the air standard properties, which is like which are given there. I suggest one thing here. Actually, the given Reynolds number in the paper is like 2 million. But when I compare the Reynolds number, when I use the Reynolds number formula, and I put these things here, like velocity is 10 meter per second, diameter is 2.5 given there. Like here you can see diameter is 2.5. But when I put the value of the density and viscosity of the air, I cannot actually have the 2 million here. So now my point is that to make it 2 million, so we have to change some values here, actually. Okay. So what we should be doing here is that my idea is that I will keep the same density, same Reynolds number. So I will put a formula like this. 1.225, 10 to 2.5 divided by viscosity. Okay. So we should calculate the viscosity that should give us the 2 million Reynolds number. So the mu is equal to 1.225 into 10 into 2.5 divided by 2 into 10 power 6. So mu will be equal to this one. 1.225 into 10 into 2.5 divided by 2. So this is equal to the how much? 15.3125. So you can make it like a 1.53125 10 power minus 5 Pascal second. Okay. So when I open the fluent, so I will just go to material properties and I will change them to 1.53125. Yes. So I will change the properties of air. So I will keep the same density, but I will put the viscosity as this one. This is the 1.53125. Okay, click on change, create, and close. Okay. Then in the boundary condition, I'm going to put the at the inlet, I'm going to put the velocity as equal to the 10 meter per second. So normal to the boundary, which is specified over here. Okay. Apply and close. And in the models, I will keep the SST model by default. Materials are there in the cell zone condition. I'm going to make the fixed domain as a fixed. They are fixed already. Okay. Here air is there, but I will be putting the RPM for the rotating domain. So you can put the values either in terms like we are going to use a mesh motion. So I will not use the mesh motion first, but I will use the first frame motion. I will discuss about this thing. So a difference between the mesh motion and the frame motion. Let me tell you what's the difference there. So the frame motion is actually the fixed position in time and space. I'm not saying that we cannot run the transit simulation, but the flow will be like at that time it is frozen there. That's why sometimes they also call that solution method as the frozen rotor. Okay, and it's a steady state. So what is the point here? Point is that if you for example, here the wind turbines blades have their positions like here. Okay, and other wind turbine blade will have the position like so they will be fixed there. They will be fixed there. They will be fixed in the time and definitely in the space. So whatever flow is being done is now it is like only we are getting torque value for the one single position. They're not changing their position. So this is like a frame motion. But if you go with the second option, that is a mesh motion, so it is like like a different positions. Like now the second position of wind turbine blade will be like this one. So what is going to happen is that like frame motion, mesh motion. So let me tell you difference between them. So it's like moving the blade to the some like a 1 degree. We change the usually speaking, we change the 1 degree in a one time step. So we change the 1 degree, and then we run the solution. We get a solution on that location or the location of the wind turbine blade. We solve the case there, and we get the torque value. Then we again advance geometry by the 1 degree. Not limited to 1 degree. We can advance by the 0.5 degree. We can advance by the 2 degrees. Now depends on the solution accuracy. So which one is going to give us a more accurate solution? We will take that one. Okay. So now question is that so mesh motion actually is like a changing position of the wind turbine blade in the circular fashion, and can then get the data on the each and every location. So torque will be varying actually. So that thing we can do also manually, means that we can move the like every time we move the our turbine blade. But thing is that like if we make interfaces, and after making interfaces, if you rotate the geometry like mesh, we can rotate always. So every time you have to go to the domain, we have to go to the like a transform and a rotate. And every time you have to delete the interfaces, rotate the inner domain by the 1 degree, the rotating domain. Again, come back here and make the like interfaces there, and again solve the case. And then you have to keep the data yourself. So you have to save the each and every file there and get data for the each and every position. This will be like a very cumbersome job. You have to take care of 360 files, and this is only for the one iteration, one revolution. Maybe for getting the proper converge solution, you have to solve for at least for 5 to 10 revolutions. So 10 revolution means that you have to keep the like a 3,600 files. This will be very cumbersome job, and storing that this much files will be require a lot of data, and also it will be like a full-time job for you. Maybe for 3 months you will be sitting on your computer. So what's the point there? No point there. So that's why we use a mesh motion. It will advance the position and solve the case, and it will give you the data which we require actually, which is the torque value. So from torque and momentum are same thing. Okay. The movement around the axis is basically is a torque. Okay. So from torque, we can find out the power. That is the torque into omega will be power. So now the question is that we should go with the frame motion or mesh motion. The answer is that initially I will be solving the frame motion. Why? Because I want to get the converse solution on the one position. So once I start to rotate the geometry, it should have the converse solution from where I am going to start. So maybe on the frame position, on the fixed position, maybe the 200 to 300 iterations should be enough in the steady state mode. So once we get the converse solution, then we can use a mesh motion, and then the time step will be selected. Okay. So first we start with the frame motion, and then we convert that to the mesh motion. Okay, got it?
Yeah.
So the frame motion will be only used for the initial case, for the initial solution that we start from there. Otherwise, if you don't do that thing, then we have to like maybe 2 or 3 revolutions will be only used to get the stable solution. Okay, that's why the frame motion will help you. Okay, now you can put the data in the radians per second that we have the like determined is equal to the 20 radians per second. Okay. So that thing is there. Or you can convert the system to the revolution per minute. So that you can change it from domains and units, angular velocity, you can change it to the revolution per minute also. And now you can put the value as a RPM. So 191. It's your choice actually, your choice. Okay, so then we click on the apply and click on the close. But definitely we have to create mesh interfaces that is between the interface inner domain and the rotating domain. So we have to like make interface between what? This will be like between the inner domain and this rotating domain. So this will be the Common boundaries are here, if you remember. One interface will be here. This interface red color should work. Interface between this inner domain and the blade domain. Blade domain is rotating actually. Okay. Then we have the next boundary that is over here. No color is working. Okay, second boundary is here. And this interface between the our blade domain and the outer fixed domain. Okay. So data from the like atmospheric, we are putting the 10 meter per second. Data will be transferred to the inner domain and strike with the wind turbine blade. Then it will transfer data from up to here. Then it will now move the data from internal side of the domain, internal domain. Then it will go here. If the blades are there, like they will definitely are rotating. So they will interact with this flow. Then they interact the flow, and the flow will then leave these boundaries. Again, they will go back to the bigger domain, that is the outer fixed domain. Okay. The flow will go inside here and then it will move outside. Simple. So here we have to make the interfaces. So this is between the this interface inner domain. I can display the geometry also. So what I'm saying is that interface inner domain, which is here, and interface rotating domain and the inner domain boundary, which is also here. You can change the colors by the surface IDs. Same boundary, they are same location exactly. Okay. Second interface is the outer domain that is over here. Over here. Okay. So make interface between them. So click on create. And then outer domain, rotating domain, outer domain. So this is like a two interfaces boundary. That's all. Okay. Then in the methods, what I chose, I have to see that thing because that is after some experience. So I will look for the setup settings here. So define velocity here. Interfaces. So we choose a mesh motion. Okay. First the frame motion, then we choose the mesh motion. We will keep the coupled solver. We report definition for the torque and okay. So that's the point here. So I will keep the default settings for the solver coupled. And I will also keep the default settings here. Okay. Okay. So we are done here. Then I'm going to monitor my data for the like a boundary. That boundary is going to be sorry, not here, but the report definition. So click on new surface report and not surface, but the force report movement and movement on the wind turbine blades. Okay. Wind turbine blades and few things we have to set also. So I need to actually get directly the value. So this is the like my chart for the torque. Okay, so I also want to print to console and click on the OK. Okay, then you have to like make the boundaries, outside boundaries should be the interfaces. Okay, they are not going to form any boundary layer, so they should be like these boundaries. These boundaries will be the either no slip conditions or they will be symmetry conditions. So I have to change these boundary types from the wall to the either the slip condition, slip wall, or the symmetry boundary condition. So in the boundary conditions, the bottom will be the symmetry. It's your choice. Symmetry with the slip condition is the same as a symmetry boundary condition. So the top. Okay, and initialize. So I will initialize from here. Okay, so then we have to like hit the, okay. The time step calculation is very important. So the basic point of time step calculation is here, given here. So you can see that actually this wind turbine now given TSR is a 2.5. So I can write down the formula for TSR, which is omega R upon velocity in for the wind. And I have drawn the circles, the circular path of wind turbine they are following. So diameter circumference is this one, and half of value is the radius, and the tangent velocity is the omega into R. A linear velocity is omega into R. So I can find out the omega by this formula. So omega is 20 radians per second. Tangent velocity will be the omega into R, that is equal to the 20 into 1.25. It's a 25 meter per second. Okay. Turbine diameter is 2.5. Circumference will be pi d, or you can also use 2 pi r. So this is a 7.85 meters. And time to complete one revolution. So, like if we divide this the distance by the velocity, we can get a time that will be used, or this will be time it will spend to complete one revolution. Okay, this is equal to 3.314 seconds. Now, this is the time we get for the if the wind turbine blade is here, it will make the one revolution. It will come back here. Okay, in this much time, that is a 0.314 seconds. But actually, what we want, if we solve in the one time step like 3.314 5, this will be like 0.314 seconds. This will be like in the first time step is here, then second time step this will be again back to the here. So we cannot get solution on different locations. So the idea is that wind turbines that it should advance by the 1 degree. So it means that the total time should be divided into 360 time steps, because in the complete circle there are 60 degrees. So we should divide them into the like 360 number of steps. So I will divide this total time into the 360 time steps. Okay. So the value I'm going to get for one time step is the 0.4087222. That value you have to put over here. So discard. So I'm going to put the value as, okay, sorry, one more thing. Right now, this is the steady state. So I'm going to run the like a 300 iterations. And when we change them to this transient, then I will use a time step here. Okay. So now simply click on calculate. And this is now, this is for the all three blades. Okay. So all three blades, maybe they are producing the negative value, positive value. It depends. Okay, so solution is done. So we can see it still is converging. You can run for the like a more iterations. Okay, and this is very much obvious. This will not converge to the single value because this is like a transient solution. Okay, I will take the 5 minutes break. I will come back. Okay, I'll discuss this thing.
Okay, thank you. Yeah.
5 minutes only.
Okay.
Okay, so we have the now solution here. So let's check the results. Okay. So I will go for the contour plots for the velocity. And we have the like some indication that something is happening there. So right now, if you take a look here, if you take a look on the pressure contours also, so I get the idea that the domain size is not enough in the like lateral boundaries here. Are you getting my point? The pressure is actually striking on the boundaries here. Here. So domain size should be large enough so that the internal flow should not reach the boundaries. It should not affect the boundary flows. Okay. It means the domain size is small. It is not affecting the inlet boundary. It is not affecting the outlet boundary. It is only affecting these two boundaries. So I think that 10D should be also done here. So I'm going to change the boundaries here. So for that, I will go to the geometry. Okay, and plane number 4. This one, okay? So this should be like a 5D. So calculate. So 2.5 into 5 into 1000. It should be 12,500, okay? So 12,500. And click on generate, okay? And now save the file. Take to the meshing software. And definitely you have to like make the new mesh for the new geometry. Can you hear me?
Yeah.
Okay. So simply generate the mesh and update everything. Okay, and update. Simple. And you can read the mesh file by clicking on the refresh input data file. Okay, so let's check the boundary conditions. Uh, Top and bottom, they are the symmetry. Inlet is inlet. So just check the boundary condition here as well. And it should be 10 meter per second. Yes, correct. Outlet is the pressure outlet. Everything else is there. Okay, okay, okay. Okay. So now again run the calculation. Okay, let's check the control plots. So now we don't get any reflection from the interior domain to the outside boundaries. Okay. Same is true with the velocity. Okay, so now we can change the our case to the transient case. So what I'm going to do is that I'm going to right now I will go to journal, and from here I will click on transient. Okay, number one. Okay, then I will go to the cell zone conditions, and I change the my rotating domain from the frame motion to the mesh motion. This will be like initial condition for the mesh motion simulation. So there are the two names frame motion and mesh motion. So generally speaking, what they call them in the literature, I will tell you. The frame motion, they call that thing as the frozen rotor. And the mesh motion is a sliding mesh, because the mesh is sliding over the second mesh. So that's why this is called the sliding mesh. Okay. So I will go to the rotating domain, double click here. So I will directly, instead of going to the mesh motion, I can directly copy to mesh motion. So click here, simple. It will change to the mesh motion. Okay. Apply and close. Okay, in my point of view, if I tell you that I don't think so that a couple solver will be helpful in this case. Secondly, I'm going to use the second order implicit for the time formulation, but I think the simple will be better for this case as compared to the coupled, because coupled will take the more memory. It will take more time for each and every iteration. And I have seen recently that the simple method and the coupled method, they give almost same solution. So there's no point of actually having the more memory use and the more time use for the one iteration. So that's why I'm changing it back to the simple. Okay. And now you have to put the time step here, that is equal to the how much? The time step is the point 408. I'm just copying it. Okay. So copy the time step and put over here. Okay, number of time steps. I am going to actually the way we get the data from the wind turbine simulation is that we get the data for the one evaluation. Okay, so that is at least. So it should be for the one evaluation. So the people in the scientific community, they say that it's the one evaluation data is required there. Okay, so to average out data, they say that you should be taking data for at least for the 5 cycles. Means that you will get the average data for the 5 cycles. So
Mhm.
sometimes maybe there are some inaccuracies there, so they can average out in the over the span of the 5 cycles. Okay, so that's why the 5 cycles means the one cycle will be, because we are putting the one time step, one delta t is equal to 1 degree advancement. So one cycle means it's 360 degrees, and which is equal to 360 time steps. So the 5 cycles means this will be equal to the 5 into the 360, which is equal to 360 into 5. So, but this is for the last data. It means that when you are going to get data, that is for the last 5 cycles. This is that theory. So now, right now we run the case with initially we run the case with the steady state. So I think solution is stabilized. Now we can change to the transient solution. So maybe there are the extra revolution required where the solution data will be adjusting to the transient environment. Okay, are you getting my point? So I will add the 5 more cycles. Means that this will be like a 5 plus 5, 10 cycles will be there. And we should solve this one for the 60 into 10, 3600 time steps. Okay. So how the question is that how we actually access the convergence for the transient case. The answer is that for transient simulation, what we do is that actually transient simulation means solution will be varying with the time. Okay. So some variable is here and there's a time here. It will vary with the time. So it can vary in any way, but we get this when the graph is like is a constant change. It's repeating itself. Okay, repeating itself. Then we say the solution is converging periodically. This is the in transient simulation we cannot have the single line. Okay, we get the periodic convergence. Periodic convergence means after some time, after some period, the solution will start to repeat itself. That is a periodic convergence, and that's when we achieve. And after that point, actually we have to run the case for the at least for 4 more cycles, 5 more cycles. So once we get this thing, so the idea is that if you go for 10 cycles, I hope that in the within the first 2 or 3 or 4 or 5 cycle maximum, solution can stabilize to the like this periodically converged solution. So it means that we can have the data for at least 5 cycles. The solution has been converged periodically completely. Okay. So I'm going to like put the how many steps I'm going to put 3600. Okay. So extrapolate variables will actually will make the solution convergence faster. Okay. Why I don't know, but it makes it faster. Okay. Now click on the calculate. So it will override the torque plot. And now we get a data with the time step. Okay. You can change it to the from the flow time and the time step is the same thing. Okay. Okay. Sorry. We did the wrong thing here. It should be the 0.0004 zeros and something like that. Okay. Okay. So, okay, now let's initialize from very beginning because we lost the data, the steady state data we lost because of wrong time step. So let's start with the like initial, again, we initialize the from the very beginning. Okay. So use hyper initialization. In both cases, in the steady state first and then the transient, are directly from transient, the both you will get the in the both ways, you get the same simulation, same results. But thing is that it may require more time to converge to the steady to the periodically converged solution if you start with the very from the very beginning. That's the only point. Okay, it was converging solution in the very less iteration, so I will stop here, and I will be going to the my monitors and I will put the some more zeros here. Okay, again run calculation. Okay, again we can stop here. What I want is that I want that actually the here I want the time steps. Okay, instead of flow time, flow time will be like if you run the 10 time step, the time will be the 10 into time step. Simple. Okay, so here I am going to go to the report plots, torque plot, and make it the time step, and again calculate. Okay, I stop solution here. I just want to check that if I like check the solution, you can see that we have the like different blade position is right now with us. Okay. Initially, the blade was like first blade was here, second blade was here, third was here. Now they are changing their position. You can see it, right? Okay, so it is moving. Actually, this is moving. Okay, so we can continue with the simulation. So, but the behavior, like if you take a look here, what I want this behavior actually from solution. This behavior initially, like it was running in this way, but after some time it will establish into the like a transient behavior, and then once it is go through that transient behavior, initial transient, they will stabilize to the product convergence, like it is repeating itself. Okay, so let's wait for the solution. You can see that the data is now actually going for the, but for by this time, I think we should be at least have the one half population completed. Okay, like this. Okay, so continue. Okay, one thing is that is that there are three zeros, but there we put the four zeros. 1 minute. It should be 10 power minus 4, right? Okay, calculate again. Because it only advances very few positions. That's was indication that something was wrong here. Okay, you can see the now the difference here. Okay. Okay, floating error. Solution diverged. I don't know why solution diverged here. Okay, let's start again. So I will again initialize. Okay, it means that the couple solver is the solution. Okay, so let's initialize. That's the problem. Actually, that's why I written there that couple solver was there. So sometimes the some solvers they may not work. Okay, so I'm changing to the couple solver.
Mm-hmm.
Again, the same problem. Okay, tomorrow again we will sit together and we will sort out this problem. Okay, something is wrong. Okay, one more chance here. So I will start with first order implicit, and I will put everything as a first order. Okay, so this can solve the problem actually. Again, I can see the convergence problems here. This indicates some problem is there. So let me check. Loss is very high. This indicates that something is wrong here actually. Okay, we will sort out this problem tomorrow. Okay,
Mm.
something
Yeah.
is wrong here. Okay, so see you tomorrow.
Ah, okay. Yeah.
Okay.